And we partnered with the Ghana Sustainable Aid Project, Hannah Davis and Melissa Davis, who received funding from the Gates Foundation to put forth this project. I should say something about the Ghana Sustainable Aid Project. The timeline here. It was founded in 2005-2006. It had the express purpose of dealing with education, especially the education of girls in the village in Ghana, and trying to deal with the obstacles to girls' education. And among those obstacles, as everyone in this audience is well aware, is the absence of effective sanitation in these communities. It then moved through, considered a public toilet before it got fully involved with trying to deal with the sanitation issues facing that community. At that point, the head of the GSAP is actually my granddaughter, and she affectionately said, "Poppy, maybe you can help us. You're doing work in your lab on sanitation, maybe you can help us." Well, at first I said, public toilet is probably not going to contribute very much, one public toilet, to this community. But we had been working on a broader range of toilet models. And so I said that I would get involved, and the next thing we know, that they applied for this the GCE report. In 2009, while on sabbatical teaching at the University of Ghana, I started visiting the leading technology systems, facilities, which was the KVIP in Ghana, the Kamasi Ventilated Improved Pit Latrine, which was funded by USAID. Dr. Alfred Wright, a noted sanitation engineer, developed that system. I visited 18 of them. Of the 18 that I visited, 17 were, everyone would describe as completely failed. One was working, and I was very surprised at that. The one that was working kept me awake at night. I visited this one village where this KVIP system seemed to be functioning beautifully. And I decided that I couldn't lose much more sleep, so 3 or 4 weeks later I drove back and hopped on a trotro and drove back and visited again, and it too was failing. And so I asked one of the residents, what happened? What do you mean? And I said, well, I was here a month ago and this system was functioning beautifully. And she says, well, it was only a week old at that time. So it too had failed. I'm going to just talk a little bit about the technology, our approach here, and it's a little different than what we heard in the earlier part of this afternoon session, where there was some emphasis on anaerobic digestion. Here, the emphasis will be on aerobic digestion. We'll talk a little bit about the prototypes and that we built, our observations, and some lessons that we learned, and then how we plan to go forward. So I have a few slides here called the product, the process, and the price. If you don't have to take some notes, I have a little brochure that captures these three or four slides, and you're free to take one, or if one of the attendants wants to pass them around, that's fine also. At any rate, each of the facilities that we build has a sink inside the facility with a small day tank featuring a handle-free aerator. The dirtiest place in every toilet in probably every country in the world is the stall door handle, which is highly contaminated. The flush handle, it has a flush handle, and also the sink faucet. When we do surface fecal coli tests on those, they're really nasty. And so we decided to get rid of the faucet handle and use an aerator. And the two types that we work with, one is this little mechanically adjustable push-button aerator that releases water low flow for a short period of time, programmable period of time, between 2 and 18 seconds. And then another is a famous little bar aerator, which has now been improved to the point where it's almost washerless. And so when you displace it, it does water. When you're washing and scrubbing your hands, let it go, it stops. And so these are both low-flow products. This goes into an aerobic digester that emphasizes the use of macroorganisms. The major organism, the one that we use in every digester, is E. fetida. which is found pretty much everywhere. Inside the filter, inside the digester, there's a dewatering filter made of an aggregate. Rapidly dewaters the mass. The resulting leachate is released currently to the environment, but given the fact that it's a small amount of water, it's equivalent to a very small fraction of a leaching field, a very tiny leaching field. Although we are working on what we call leachate. We have several different methods that we're going to apply to treat that water as well. And then, of course, the solids are aerobically digested using not just E. foetida, but also other macroorganisms that are available. I'll say a word about that in just a second. So, you know, if you look at the volume/mass of materials into the system, 124 grams of feces are transformed into less than 15 grams through this aerobic process. The mass reduction is phenomenal. So you're dealing with an extremely small amount of final mass. It is now becoming pretty well understood that vermiculture does offer not only a viable alternative, but in many cases a preferred alternative for digestion. Pathogen destruction, compost quality, and operational cost. As I mentioned, we use E. foetida, the red wiggler worm, but we also have accidentally introduced the dung beetle. There's one variety that is especially attracted to human waste. They each operate in different portions of the digester. I was telling someone about the E. foetida. Why are the earthworms gathering on the outside part of our filter? And until we solve the Poisson equation in 3 dimensions, I'm a physicist, by the way, we solved that equation with the boundary conditions, we didn't know why the earthworms are gathering in this outer region. Well, when we looked at the results of those solutions, the solutions of those equations, we noticed that there's this little band of temperature, not very different than the temperature in the rest of the digester, but different enough for it to be a very hospitable place for the worms. But the interesting thing here is that our digester works in Ghana between these temperatures. It's about maybe 26 to 33 or something, and that turns out to be there are many macroorganisms that turn out to be have preferences, temperature preferences that are in that range. So we mentioned the dung beetle. I hate to mention the German cockroach, but maybe we found a use for that pest after all. The black soldier fly, and there was a paper yesterday. Cecilia gave a paper on the Swedish College of Agriculture. Gave a wonderful paper on black soldier fly, which I missed, but I caught up with her at the bar last night, and we chatted a little bit about that. And then we're also looking at things like wood lice, which also can find their way into this environment. The price, $1,200 for the prototypes. It's way too much. And that's for a system that is good for about 30 users per day. In terms of lifespan costs, very quickly, if we use a 15-year lifespan, which most of the industry don't want us to use, they want us to use a 5-year lifespan. But based on a 15-year lifespan, it's about 2.5 to 2.9 cents per user per day, and that includes, in fact, most of the cost is toilet tissue, towels, soap, and so on. If you bring those costs in, as a matter of fact, if you bring those costs in, I would say that we will never get to Bill Gates' target of 1 penny per user per day. If you leave it out, you just include the sort of amortizing the cost of the system with a little bit of maintenance, perhaps. But it turns out soap costs for washing hands, and that's got to be part of the sanitation solution, washing hands. You bring that in, and you bring the use of toilet tissue into it. It can be very high. On the basis of a 5-year basis, it's about if we leave out those costs, it's about 3.3 to 3.8 cents per user per day, and this is on the assumption that the user is borrowing money to buy the toilet. Borrowing at the rate of 20% per year in the case of the 3.3 cents, 30% per year in the case of 3.8 cents. So we installed 4 single-stall toilets, family block toilets, that are between 17 and maybe 30 uses per day. We installed a 5-stall school toilet in Pakwasi and also a 10-stall public toilet. The 10-stall public toilet has only been operating for about 3 months now. The 3 of the 4 toilets are in a fairly dense area of a village known as Pakwasi in Ghana, about an hour outside of Accra, in the Western region. And so the exterior of the toilet looks just pretty much like any single-stall toilet. The interior has a fixture which is made from poured concrete, ferro-concrete. In fact, the entire digester, the prototypes are all made from ferro-concrete. We did some surface fecal coli counts early on, first on the lower sections here with the higher bars. These are all from existing toilet facilities in the village that many of the people using our toilets have used before they got their own. And you notice that generally we looked at things like the door handle, the sink, the flushing handle, the surface of the toilet seat or squat surface. And at the top are our microflush school toilets and the microflush household toilets. And I mean, in general, we're pleased with those results. They're perhaps save for one school toilet. They are lower fecal coli counts than the other toilets in the village. But we wondered, why is the school toilet so much less than our household toilet? So we drilled down on that a little bit, and here are the fecal coli counts on the surfaces on door handle, sink, and toilet seat. And if you notice, if you take a look at this, the school is in red, so those numbers are definitely smaller than those on the school toilet. And yet, of course, if we drew the other toilet facilities on the same slide, it would be off the right-hand side of the room. But nevertheless, we tried to look at this a little bit more carefully. And in the process of constructing these toilets, the installer decided that when he built the household toilets, he didn't want to use these valves. He didn't know what they were. And unfortunately, the contractor, there was no supervision of this installer. And so in the household toilets, he put a sink inside with an ordinary faucet. Also left off the day tank, so the faucet was useless. We were very disappointed about that, but nevertheless we learned quite a bit from this. In the school toilets, because we did it ourselves, we did install the little push-button systems. And so it's not too surprising that the school toilets were a little cleaner, and especially door handles and sink areas. So we took a look at those 4 systems that had been installed without the push button. In 3 cases, they put a wash bucket inside the toilet with a little scoop for washing hands. And I should mention, as I mentioned earlier, that that gray water is used to do the next flush of the toilet. But the interesting thing is, when you look at when the bucket was outside, take a look at the door handle fecal coli counts, and the sink edge for the fecal coli counts. They're much higher. This is hardly statistically significant yet, but it does indicate a possible trend. Odor levels. When people visit our toilets, they say, "Where is the toilet?" Because there is no odor and there are no flies. Anecdotal evidence on only on the single stalls. People, these are quotes. We like our toilet. Our family, even our children, like the toilet. We don't ever want to take it away. We'll never go back to using the KVIP. In response to how is the toilet, it's really nice. One family who's been using this now for over 2 years said, you know, one of the children who was always getting sick with a stomach ailment and diarrhea has stopped getting sick, and we don't know why. And in fact, he didn't start getting sick again until he went back to school. Kind of interesting. The first person to get a toilet, we kept a close eye on the first family. And the interesting thing that happened was I called this fellow, I'll only mention his first name. I called Sammy one day. I said, Sammy, how's the toilet going? Oh, he says, our family loves it. Probably really likes this toilet. He says, of course, we haven't used it yet. And I said, well, why haven't you used it? He said, well, he was hesitant. He said, we don't know how. We don't know how. So rather than sit down, I'm an experimental scientist, rather than sit down and write out instructions, go and show him, I did nothing except for put up this little plasticized poster on the inside of the stall door. The next day, he called and said, wow, everybody's using it. And so this is mostly icons on how to use the toilet. Some of the lessons learned on the household prototypes, a reluctance to install the microflush biofil systems with the push-button bar. The plumbers, for some reason, just didn't like doing it. It's something that they said, well, we have to sort of stand behind our work, and so this is risky. They preferred, in fact, most of them preferred just using the bucket and scoop method, or the pour flush method. The market for toilets is strong. Everyone who has seen these wants one. Not everyone can afford one. As a matter of fact, those people who have one of our prototypes, honestly, if you met them, you would say these individuals are poor, but they're not. They're not very poor. Their household incomes are 10 or 12 US dollars per day, whereas the target of GSAP, the Ghana Sustainable Aid Project, those people who are in the bottom 2 quintiles, in Ghana that's about 700 to 1,200 US dollars per year, a couple, $2 or $3 per day. It's, I guess the biggest lesson is the little things, you know, the aerator, the day tank, the plumbing, they're as important as the technology. The school toilets, as I mentioned, the school toilets do have the push-button aerators, and in the wash business, schools are sort of a whole separate subsection. The issues that you deal with in school toilets are quite different than the issues that you deal with in a household. But we had in the school toilet installations the same installation stubbornness. You know, plumbing that was done poorly. I had a plumber who installed, we restored a well and tank that was not functioning, and he brought a pipe down underground into the school toilet and then brought it up over the top of the tank and wondered why it doesn't work. So there are things of that sort that get in the way of the local skills, the local culture of installation. There are also the same things that the wash people have seen in school toilets, the issue of toilet issues, soap, cleaning, and maintenance. But the good news is that for the most part, GSAP has overcome these challenges in the community. We reinstalled the pipe to make sure that the tank worked. We made sure that children were shown how to use the toilets, and that soap was made available to them. The 10-stall public toilet is just opening. I'll tell you the interesting, I'm sort of emphasizing the things that went wrong. So much went right, but a few of the things that went wrong. If you take a close look at the gutters here, they're installed backwards. They don't flow to the tank. So in spite of your best design techniques and so on, you wind up with workmanship that just doesn't work. And so sometimes you have to undo and redo and so on. Let me just get to the last part here, talking about the physical factors. In the order of importance, the physical things, we know that a system is not just the nuts and bolts, it's the people, the processes, the procedure. But the first thing I think is the toilet technology. On the physical side, if you have bad technology, everything else can be right, it's all wrong. So the technology is important, at least on the physical side. The less important is the interior hand wash, but that I think also has a certain level of importance. Accessories, day tank, faucetless aerator, a little less important than the overall technology. But last on that list is the facility interior, the walls, the floor, and so on. Those are I think, the least important factors. In fact, if you look at some of these examples, here's a toilet in Texas. The walls are not tile. The walls are actually glass, one-way glass. Can you imagine using that toilet? The good news is that they've got it right. They've got the wash basin inside. Or someone got really creative. Can you imagine walking out of the New Year's Eve party and using the restroom and walking in there? Wow, that would sober you up in a hurry. Toilet ownership is a function of three things: functionality, affordability, and installability. And we have two models for scale-up. My colleague, Kweku Ano in Ghana, and I, through the generosity of the Gates Foundation, were able to bring our separate technologies together, get them out of the lab, put them in the field, and I think we have shown that they work. There's still lots of work to be done. But in moving forward, Kweku owns a company called biofil in Ghana. He's going to take the factory centralized approach, building lots of toilets in one factory and deploying them and maintaining them from that factory. It has the benefit of a high degree of quality control, the future benefits of mass production, but it also has the difficulties of high startup costs, transportation costs, and higher end user costs. On the GSAP side, we're taking the on-site fabrication approach. I guess, maybe to put it in one word, we want to see microflush biofil as one element in the open source of sanitation. So we'd like to see this be analogous to what's happened in open source computing, where you put it out there and you let it self-improve. And to that end, we have actually started building a manual on how to fabricate the microflush toilet, microflush ready toilet. And going forward, all of our research at Providence College is aimed at looking at digesters, housing, filter efficiencies, and so on. And on the GSAP side, it's identifying local partners, NGOs that can identify a craftsman who is looking to create an enterprise out of building toilets. And we will help to support that. I just want to acknowledge the Bill and Melinda Gates Foundation and many partners, the staff in Bokwasi, Sammy Java and Eric Gajiman, and many students. The most recent, Colin McDonough, who was co-patented the valve with me, Robert Kretz, Ashman Caldell, Katie Foote. All these folks are now in graduate programs someplace in the United States. I've also been partnering with a microbiologist, Dr. Brett Pollock, and of course biofil.com, who was the contractor on this process, and finally EcoWise Technologies. Thank you very much.